Okay, welcome everyone to my continuation of what are my favorite theorems. My very biased collection, as usual. Well, actually, today it's not really a theorem, it's more like an idea that I would like to sell. So what are diagram algebras? Of course, I'm going to explain what diagram algebras are, at least from my perspective, because there is no really a well-established definition of what a diagram algebra is. But kind of the point I would like to sell is that there's a very nice class of diagram algebras, which are, given by pictures, so a very nice class of algebras given by pictures that kind of arise in many fields, or arose from many fields, actually, of mathematics and physics and other stuff, and have been very popular in the past 30 years or so, although they're around for quite a while. So on the last slide, I would like to, explain a little bit how I understand the the history, not the definition, the history of those diagram algebras. Of course, this is biased and very incomplete, but I'm still trying my best. So if you know Feynman diagrams or Penrose diagrams or all that stuff, that's kind of related, and I'm trying to explain how it's related. So my approach to motivate diagram algebras is not the original one. So just what I'm trying to explain fits very nicely, I think, works very nicely, at least for me. Kind of brings topology into the picture, but be careful, as I said, is not the original motivation where those algebras came from. In some sense, they came from representation theory and mathematical physics. In some other sense, they come from various incarnations of some nice algebra that interpreted in terms of pictures. And as I said, they became very popular about 30 years ago, maybe 40 years ago. So when there was this breakthrough with the Jones polynomial, so Vaughan Jones got the Fields Medal for the discovery of the Jones polynomial, which is about 30 whatever-ish years ago by now. And kind of related was this breakthrough in diagrammatic notation for various types of objects, which is now very popular. But it's still kind of relatively modern mathematics in the sense that it hasn't entered all fields. So it's most present in, as I said, mathematical physics and parts of algebra, parts of combinatorics, and so on. Anyway, it's a lot of fun. And of course, topology, because my motivation today is topology. Anyway, it's a lot of fun. And here's my motivation. Again, there's a slight warning here that this motivation is not the original motivation to introduce those algebras, but we will talk about the history at the very end of the video. Okay, so here's the idea, or how I would like to present diagram algebras. So I would like to use this idea of cobordism, which is just a certain topological object in this notation read from left to right. So a cobordism is a topological version of a map. And I would like to, formally it's the following. The cobordism is W in this picture, and it's a map, if you want, from a manifold M to a manifold N. And it's, let's say this is of dimension N, this is of dimension N as well. Then the cobordism itself is n+1 dimensional manifold connecting the two. And up to some technicalities to make sure that you know what a source and a target is, you can see this actually as a map from M to N. And because it's a map, there should be a gluing operation or a composition operation, and this is really just gluing. So I could have another one going from the same N manifold to somewhere else. God knows what it does. Maybe some handles here, maybe it goes to a circle or whatever. But I could just glue W and W prime along the common boundary here and get a new manifold WW prime, which would go from M to whatever I would like to call my output here, X, which would go from N to X. So here's an example of this. So here you start with 5 circles. You have this manifold that goes all the way along to 1 circle. So 5 to 1. And then you have this guy, which goes from 1 to 1. And then you have this guy, which goes from 1 to 4. So in total, you get a map from 5 to 4 circles. And circle is, of course, just a very, very easy manifold, in this case, a one-dimensional manifold. So up to some appropriate care, you need to be very careful with the definition and everything involved. But basically, this is the idea. So cobordism in topology is a manifold with boundary. Boundary is, again, a manifold. And you organize the boundary in such a way that you can think of it as a map from certain manifolds to certain manifolds. And that's a cobordism. And the nice fact about Cobordisms is really this picture here, so that you can easily compose them by just gluing along the common boundary. So composition here always gives you a natural multiplication structure on those pictures. Strictly speaking, they're not pictures, they're really geometric topological objects, potentially in very high dimensional spaces, but kind of in my illustrations, they will always be pictures because that's what I can draw. But this in principle works in any dimension, like as I said, dimension 500, dimension 500, dimension 500 plus 1. This here is dimension 2, so the W is of dimension 2 and the manifold is of dimension 1. Because the manifold here is the boundary manifold is just a circle. And well, these guys are surfaces, for example, this little pair of pens here. And it took a while, but people understood quite early on in the theory of Cobordisms that Cobordisms kind of correspond nicely to algebraic operations. So here I have my nice pictures from before again, including now a cup and a cap, and the pair of pens from before. So again, a map from 2 to 1, a map from 1 to 2, a map from the empty manifold, which is 0 if you want, to 1, a map from 1 to 0. And you can also think of it in terms of nicer Feynman type two-dimensional diagrams, kind of the spine, if you want, of those pictures. And you get those merging operations, the splitting operation, and the annihilation operation, and the creation operation. That's how physicists maybe would call it, or would have called it, probably still nowadays call it. And on the algebraic operation, you could think of it as multiplication, and you could think of it as a, well, whatever kind of dual multiplication, a co-multiplication. So from one object to two objects, so from A to A tensor A, or from the multiplication is more the familiar one, from AA to A, and so on. And all the natural axioms are then just axioms on Cobordisms. So slightly silly. So I stole the picture from above, and the time from the picture from above goes from left to right. And in my notation, usually the time goes from bottom to top. There will be there are 4 different possibilities how to do it, and you will find all 4 of them in the literature: reading from bottom to top, reading from left to right, reading from right to left, or reading from top to bottom. That's just how it is. Anyway, so we can, I hope at least, we can easily turn our heads and think of the bottom pictures as being the top pictures, or the top pictures as being the bottom pictures. Anyway, so for example, associativity takes this really nice relation here. So this is associativity. So we have an A, and you multiply it to a BC, right? So here BC, and here you have an AB, and you multiply it first, and then you multiply it to a C, and the outcome is the same. So this is the associativity relation in terms of diagrams, and you get those nice relations. And if you draw them in terms of pairs of pens, you actually will see that this holds just as a topological relation on those Cobordisms, very similar to the unit, co-unit axioms, and so on. So in some sense, and as I said, people understood this pretty early on, these topological objects called Cobordisms work kind of modeling algebra. Yeah, so we're naturally modeling multiplications, associativity, unitality, all that stuff. And if you have a specific algebra, then you would force extra information, extra relations on your Cobordisms, and you basically can mimic all algebras. You can realize all algebras using those pictures. That's not quite true, but it's kind of true enough for this video. And this is kind of the starting to define diagram algebras. So we have this whole machinery coming from topology of Cobordisms, natural composition, gluing topological structures, mimicking algebraic relations. So why not use it to define some algebras and then hope that those algebras have some nice intrinsic structure because they come from and was kind of defined naturally using these ideas from topology. And that's what I'm going to do now. Just the real difference is that I'm zooming in into a very, very trivial part of this picture. So as I said, this picture is in any dimension, basically, and I'm zooming in to n being 0. So my boundary will be points, 0-dimensional manifolds, and my Cobordisms will just be lines. So here's an example, and it's called the Brauer algebra, or Brauer, whatever, Brauer diagrams. Again, my time direction goes in this direction because I don't know, that's just the way I would like to read diagrams. As I said, some other people read in different ways, just be careful. Anyway, so this is a cobordism from points at the bottom, in this case 6, to points at the top. Okay, in this case 6. I could write down a Brauer category where I could vary the number of points, but I will focus on the algebra where I just have the same number of points at the bottom and at the top. So this is an element of my Brauer algebra and 6 strengths. And it's really just a cobordism picture. It has 0-dimensional manifolds at the bottom, 0-dimensional manifolds at the top, and 1-dimensional manifolds, which are really just lines, just intervals connecting them in this fashion here. So you really just have intervals connecting all the points. And this is an abstract picture, so there secretly is no intersection, and all that matters is what point is connected to what point. And gluing defines a natural multiplication on those diagrams. So I can glue the bottom picture and the top picture together because they have a common boundary, namely a certain number of points, 6 in this case. And this defines me a new picture, which is a Brauer diagram, and this is the multiplication in the Brauer algebra. There's some mild catch here. So in order to make everything finite dimensional, you need to get rid of circles, because the internal components, because otherwise you could have arbitrary many internal components, and you would get arbitrary many diagrams, and it's certainly not finite anymore. Finite is usually much nicer from the viewpoint of algebra. So the trick here is, and it's kind of a nice deformation trick if you want, to get rid of all internal components, like this purple colored circle, by evaluating them to your favorite pre-chosen parameter. So you see this little delta here in my notation, that's a pre-chosen parameter that I would like to associate to all the circles, right? So whenever you see a circle, you get a parameter delta. When you would see 2 circles, you will get parameter delta squared and so on. 3 circles, you would get a parameter delta cubed and so on. And it doesn't matter, I said again. So this is abstract. So although I draw plane pictures, so in the plane, actually it's abstract. So this purple thing is just a circle. You can just pull it out. And that's a Brauer algebra. It's really just 1-dimensional cobordism pictures from endpoints to endpoints. And it gets a natural structure of an algebra by using this idea of just gluing things together. And that's kind of the theorem. So for diagram algebras, and let's say these are algebras modeled on some version of Cobordisms, you always get an algebra, which is not quite trivial because you have this parameters floating around, if you remember here. So you need to be a little bit careful with associativity, but basically associativity will be some nice topological argument as before. And people have played around. So Brauer is kind of the classical example. From the 1930s, way before Cobordisms. So Brauer has had a really different reason to study those algebras, but maybe this is, as I said, my motivation. So Brauer is here in this little picture. So there's zillions of other diagram algebras that you can try. You could try Brauer without intersections, and you would get something that people call Temperley-Lieb. You can try Brauer, but now you allow these little cups. Remember that those little dots were just little cups, right? So this one here is just this cup, and this one here is just this. And you could do this, or more fancy things, and you leave the world of manifolds, but you have CW complexes here, for example. In this picture, you have a local component which does this along a point. That's not a manifold anymore, but kind of always kind of the same idea works. And there is this huge bunch of diagram algebras which appear everywhere, somewhere in combinatorics and quantum algebra, mathematical physics, and representation theory, and they're really powerful and really well studied. And usually they count something nice. For example, the dimension of the Brauer algebra is some nice double factorial and so on. So some nice counting formulas, some really beautiful topological pictures involved, and gives you a huge class of cool examples that you can study. And yeah, let me talk a little bit about the history. So the history of diagrammatic notation, I'm not quite sure, but it goes back to quite a while. So one of the earliest references I know are Gauss's handwritten notes. So Gauss was a bit, let's say, very different than modern mathematics and sciences. So modern mathematics and sciences are basically published this idea of publish or perish, which people take very, very seriously, including myself. So there are a lot of, including myself, I should say it more clearly. So there are a lot of really, really useless papers, including my papers out there, because there is this idea of publish or perish. And Gauss was really kind of the opposite. So Gauss didn't really publish a lot, but rather has almost everything in some handwritten notes floating around somewhere. So if you look for, and most of them are digitalized nowadays, so you can Google Gauss handwritten notes, you find quite a few of them. For example, Gauss handwritten notes on knots and braids. And Gauss thought about knots and braids quite a bit. They're huge on beautiful knot pictures and braid pictures in Gauss's notes. In particular, this one I took here, I can't quite date it back. It's kind of handwritten, I don't know. But it must have been around 1800-ish when Gauss wrote down, well, certainly there's a braid picture, which is just one of our manifold pictures, just keeping track of which strand goes over and under. It's really just a manifold picture from before, just kind of keeping track of, instead of this diagram, Gauss would have drawn this diagram or the other one by making sure the other, let me just draw the other one as well, or the other one, just kind of keeping track of which strand goes over and under. And it's not quite clear to me what Gauss is doing here. It's somehow related to magnetism and trying to compute some linking numbers or defining linking numbers for those pictures. But basically what Gauss invented is a diagram calculus in those pictures, and the associated diagram algebras are called braid groups. So this is one of the earliest references of diagram calculus. You now can do exactly the same trick as before. You can stick one of those pictures on top, you get a new picture of the same type, and so on and so on. So this is a really early reference of diagrammatic calculus, and maybe the earliest, so it's certainly the earliest I know. And I should be really careful here. So this, in the sense, is really some diagram calculus in the sense from before. Like, you really want to stack pictures, you want to see them as algebraic objects. It's not, of course, people have drawn diagrams before. You will find them in very old texts. But they always had a different meaning. They were always more like illustrating what's going on. While in this sense of diagram algebras, it's really more like the diagram algebras are the mathematics and not illustrations for the mathematics. And in that sense, maybe here Gauss is one of the earliest references, in a little bit of a hand-wavy way, because it's really hard to say. It's really hard to say from Gauss's handwritten notes, in particular if you're not a historian like me. So I'm just a no one. So it's really hard to tell. But it really looks to me like Gauss has invented diagram calculus. Anyway, so more down to earth and much later, actually, the earliest reference I found, or I know, where those diagram algebras appear in the sense of algebras. So people really have done operations on them. So here have written bases for those algebras. So these are two papers of those guys here, roughly around 1930-ish. And they came from this idea of chemical bonding. Kind of a fun thing. So it's really different from my Cobordism picture. So here's some magnetism involved, and it defines two diagram algebras. And here's some chemical bonding involved, and it defines two diagram algebras. So diagram algebras and chemical bonding. And it kind of works like this. So they model the chemical bonding. So here you have a certain type of atom, NH squared, and another one of those, NH squared. And they just model them by drawing them on a circle. So here you have H's, 4 H's along the bottom, and they have one bond, and you have the ends along the top, and they have 3 bonds, and then they draw those pictures. So the A here has 3 outgoing edges because it's 3 bond. The B here has 3 outgoing edges, and the H's have all 1 outgoing edge. And you draw those pictures. You have a diagram algebra of those pictures, which then models the chemical bonding. That's kind of cool. So I linked the papers in the description in case you want to have a look. It's kind of a very early idea. It's even before the Brauer algebra itself that I showed you, and way before Cobordisms. So this came around in the 1930s, which was after the quantum mechanics revolution, where people along Heisenberg and co. kind of figured out that a lot of quantum mechanical objects or chemical bonding objects, something like that, can be modeled using various forms of, well, representation theory of SL2 or groups like SL2 or SO3. And this is really the SL2 story. So they explain how this picture, this completely diagrammatic picture, is actually related to those matrices, those 2x2 matrices with determinant 1. It's a really nice read and a really nice paper. Anyway, I'm studying waffling, so let me summarize. So there is no definition of diagram algebras, so I was a little bit hand-wavy and just defined diagram algebras to be God-given by a Cobordism picture. But as I showed you on the last slide, this is not really where they come from. And the point is, well, that these beautiful diagram algebras, they have a lot of nice combinatorics, they have a lot of nice topology, they have a lot of nice algebra, and they kind of connect various fields in very different ways, like the magnetism picture of Gauss or the chemical bonding picture of Rumatella-Weil. And that's why I like them so much. And that's why they ended up on this list. So I hope you like them as well. Maybe you have a look at some of the references in the description. So there are plenty of those algebras around that are really studied in combinatorics or whatever, mathematical physics or chemistry even. It's really a lot of fun to play around with them. Anyway, I hope you enjoyed the video, and I also hope to see you next time.